approximately on time, so that worked out. They'll be giving you a presentation on their stuff. I don't know much about it. It's really interesting. Every time they talk, I'm like, I don't get it. Cool. Here they are. All right. So, hello. I'm Paul Orozco. I'm the team captain and president of Hornet Hyperloop. So basically, we're competing in the International SpaceX Hyperloop competition. Made it pretty far, passed quite a few of the different cuts, and we are one of the 24 international teams that have actually made the final cut. So we can actually build it and run it down over at Hawthorne. We're competing against schools like, MIT, Edinburgh, Princeton, all that cool stuff. So there's like a couple schools from like India, Germany, one from Japan, and all that. So it's pretty cool stuff. We also got quite a few different compliments from our presentation with SpaceX, such as the best controls that they had seen so far, and some kick-ass pneumatics. They're kind of chill over there, and it's honestly a really good opportunity to be able to just get a lot more experience in an actual practical setting. Because they definitely kind of like stress test us, but you got to rise to the challenge always. So pretty much we're just going to be giving you a little bit more of an overview and focusing more on the controls with Liam and Prem, and then see if you guys have any questions. And the main purpose of us talking over here is to get some programmers and pretty much develop the control systems a little bit more and actually get it working. So overview, our design philosophy is basically safety, simplicity, and efficiency. And we're trying to be able to utilize some of the different COTS components and things that have already been tested and true to be able to minimize the R&D and development time. Because, surprise, surprise, we have to basically build and develop this and test it and have it running down over there in about 6 months. So it's pretty rushed. Yeah, many of our different systems are passive. That way it reduces the time required to be able to develop the code on the control side. We've talked to some of the other teams from like last year, and that is one of the things that basically killed them, so they couldn't even run their pod. There was only about 3 teams that could actually run it full scale. So, and of course, scalability is basically only subject whenever the other things are fully kind of like accomplished. So overall, if we do the nose cone, then it's 13 feet long and about 3 3/4 feet tall, and it's about 3 feet wide. Most of it's actually the main pressure vessel, which is only about 8 feet long. The nose cone extends it off of there. And so here you can actually see it in a section view. So we have a full-scale person in there actually sitting, and we have the battery box right behind, and all the controls is going to be right underneath his feet. It might or might not be wood. We can put aluminum meshing or whatever that we really want. But like I said, there's the actual pressure vessel. So we got the interior framing on there. It's just like an airline fuselage. And then we just have aluminum wrapping around there. And we have this pusher interface in order for us to receive the propulsion by SpaceX. And the nap down over there. That way we can actually communicate with the ground control station and all of our transit systems. So we can do braking, levitation, lateral stability control, surface propulsion, surface braking, all that good stuff. So this is pretty much all the stuff that will actually have to be controlled. Then we also have to monitor, and that will all be done by the stuff that they'll talk over here. They're LPC 1769 controllers, and that'll be communicating back, controlled by an RPI. They'll talk all about that good stuff. But this is kind of a basic overview of what it all is. If you want afterwards, I can answer any questions on this, but we're going to be focusing a lot more on the controls today. Overall, it's made out of basically just aerospace quality materials. So a lot of 6061, a lot of different types of aluminum. That way it can actually be welded, like bent, and just kind of like bolted together. It's pretty cool stuff. And then the main nose cone is made out of e-glass fiberglass for weight purposes and also for cost. So it's not carbon fiber, which is a little bit more expensive. Then also to cool all of our interior components, then we're using these phase change material. So it's kind of like a buffer, like if you think back over to chemistry. So it just kind of like waits to be able to actually have the latent heat of vaporization. And so then overall, we're looking at about 890 pounds for the actual weight of our pod. We're trying to be able to cut it down even a little bit more, which I believe we've cut it down a little bit under that actually recently with a couple of new changes. And overall, we're going to be able to get a little bit above 200 miles per hour on our pod, which is pretty cool. This is based off of a 1G acceleration limit that SpaceX
basically put forth to say that they're capable of doing like 3Gs, but they're going to limit to 1G. Basically, their thing is you can only go as fast as you can actually control. So if you can't control it enough, then you can't go fast. So yeah, it's 215 miles per hour. Target stop position about 4,000 feet. The actual tube length is about 4,165, I believe. So we just have to basically stop just a little bit back of that, and then we use surface propulsion to be able to reach the exact end of which then they depressurize the actual tube, which is set to an actual vacuum of 0.125 psia. And here's a little bit of our sponsors. I wasn't able to actually get the logos for 3 of our newest ones. Yeah, we got TCOM, Saxdate, Precision Building, UEI, ANSYS, SolidWorks. We also just got DTI and Blue Collar, and then another one that I keep forgetting their name. We're definitely getting a lot more sponsors right about now, and we're going to be still contacting. I think there's a few more in the works. Oh yeah, I forgot Electromar. Forgot to put that one on there. They're doing our batteries. So, anyways, I'll go ahead and head it on off over to, I think here.
We talk about the fun stuff.
Yeah, the actual controls. Here we go.
There's multiple functions of the controls while Prem's getting ready. Are you ready to go?
Yeah, I should be ready.
Right on.
So the whole purpose of controls is to automate every single phase of the pod through its journey. So from start to the end, we want to automate every single cycle and not have any human interface come in to figure out what the pod is trying to do. In order to achieve that, we basically have built 4 sub-components. That would be the ground control station, the software that's hosted on the hardware, and then the physical hardware that talks to various sensors, and then the type of sensors we'll be reading from to figure out what environment we are in. All these are hardware redundant, so what it means is there's built-in hardware redundancies for any fault tolerance that can happen during the journey. Diving in, this is our ground control station. This is how it looks like. The front end is developed on HTML. Here's our server guy, basically leading the whole development on the ground control station. It's developed on HTML. The back end is Node.js. The whole purpose of this is to show a person or a team member standing behind the laptop or wherever the ground control station is to see what the pod is about to do. It also gives us the flexibility to diagnose anything that can happen within the pod. So when the system startups, we want to be able to control the pod from here and then ensure that every single system's working. The reason why is because once the pod is inside the tube, there is no way you can get there, and it's kind of hard because as you looked at the structure design, the controls is actually inside the pressure vessel. So in order to get there, it's going to be really hard to get it. And to ease that, we've developed the diagnostic capabilities on the HTML design right here. This shows all the details from various sensors, pressure, telemetry, velocity, along with the wheels in the propulsion system, if they're deployed or not. And you can also control them. So here's a propulsion that's forward and backward. If you press that, it basically will move the pod forward and backward. Again, to adjust a little bit when you get into the tube.
So for the app guys that are out there, this is actually just a wireframe. This was just mocked up in Sketch. If any of you guys are out there that know anything about app development or web application development, you got to have a mock-up first. This is not functioning. This is just a JPEG. So this is ideally what we're going to have like the information displayed as. We do something called information architecture. So we kind of design how the information is going to be displayed to the user and be able to be really easy to use. This is actually going to be a product. If somebody were to buy our Hyperloop off of us, they would actually be buying this piece of software from us too. So we're actually using industry standard procedures to build this, such as the wireframe. The wireframe comes first out of anything. The front end is HTML and Bootstrap, just basic markup languages. The back end server side is Node.js. We use something called the mean stack. Have anybody heard of the mean stack before? Yeah, the mean stack is MongoDB, ExpressJS, AngularJS, and Node.js. It's just an industry standard web development, application framework. Nothing is built for you. They just kind of give you the structure, and then you write the code on top from there. Go to the next slide. Let's talk about the architecture. So, Prem, if you want to explain the chart, and I kind of go.
So I'm going to start with the low level because that's where I'm coming from. That's my area of expertise, and then I'll lead off the front end to him. So starting right here, this is what we see the low level. There are 18 sensors on pod, so we'll be reading from all those sensors and then passing it through some sort of a bit computation so that that information can be understood in some part because there'll be physical raw voltages. You want to be able to figure out what that really means. From there, we'll be passing it onto a local channel, which is called Canvas. It's used in automobile industry. It's called closed area network, similar to LAN, same concepts but faster, and it's real time. In IP in LAN, you're actually trying to figure out the IP address, send it off, more protocols, the 7-layer OS. That's all not there. It's physical bit level communication. So removes a lot of OS level requirements, and you can directly manipulate those bits and send up a payload. And this can be picked up by the RPi. The RPi is capable of hosting the entire operating system and also the server that will be connected to the base station. So that sort of is the main control hub for everything. Right now, the RPi is connected on the PC back there, and then he's going to SSH into that to show you how the web page is actually being pulled up. Sort of an example to say that this entire architecture is being built as we talk right now. This is our local area network. Right now, it's being used as SAC state thing. When we go down to SpaceX, they'll give us their network that we can hop on. Same thing, nothing's going to change. It's exactly going to port out. Again, this is to show you that when we go to SpaceX, the architecture will still function. And then from here, I'll hand it off to Liam, and he's going to talk about how this builds up.
So Raspberry Pi is going to be pretty much the computer. If you guys know what a Raspberry Pi is, it's a little computer. Essentially, that Raspberry Pi is going to host a server on it. We're going to be connected to Wi-Fi, obviously. Some sort of connection will be provided by SpaceX when we get there. Right now, we're testing on, SAC state Wi-Fi. We're going to have a server on the Raspberry Pi, which is the Express.js server framework. That server is going to have a database. So all the information that comes to the Raspberry Pi via Canvas and all, your low-level sensors is going to be fed into a database. Database is called MongoDB. You can see MongoDB is connected to the server, and that is you're going to send requests to the database and get back data from the database. We're using a communication protocol called WebSocket. So what that allows is bi-communicational communications, meaning you can send commands, get commands from the pod and other devices that you have hooked up to your WebSocket. That WebSocket is going to be accessed with Node.js. The Node.js is going to create the connection and ask for data to get back and forth, and that way we can get it to the front end. You see Node.js is communicating with the server. HTML5 and Angular is actually taking that data once it's back to the local to the local web application, and then render that data on the front end. The mean stack, like I've mentioned before, MongoDB is the database, Express is the server framework, the front end and back end is Angular and Node. They're very easy to learn. Node and Angular and Express.js and MongoDB are all JavaScript friendly. With Python, we didn't go with C#. The full stack is developed in JavaScript. If you guys know anything about web development, usually JavaScript is just front end, but these frameworks allow you to write JavaScript all the way from making your button click to getting data and bringing it back. And I think that's pretty cool. It's event driven. It's super easy to learn. It's not hard. It's based on speed. If you can just follow the code logic and if you just know your basic loops and your event handlers and callbacks and all that kind of stuff are easy to learn. JavaScript is very, very easy to learn. Easy to debug also. And like I mentioned earlier, we're doing industry standard procedures. We're going to be controlling all the sourcing via GitHub. So right now, my goal for this week is to get our initial code repository set up on GitHub. So from there, if any of you guys do come to contribute, you guys will have your own branch of code. You'll be working on your own branch. You guys send us a pull request. Prem and I will validate your pull request, and then you'll finally make your code into our master repository. Very, very robust. It's making sure our code, you guys have a collaborating environment of code. If one person changes one line of code on one file, if the other person changes the other line, but lines are actually the same, who's going to keep track of that source control? You just lost the whole line of code. It gets a lot more complex than that, but that's the reason we use GitHub. Everything is lean and agile. If you see the signs for your job requirement, people want you to be agile. They want you to be lean. They don't want you wasting time writing code. You should be writing code fast in increments, getting the job done. And even any type of software development job, you're going to have assignments on a deadline. That's kind of how we are too. We have a project management PMS, project management system called Pivotal Tracker that we will be implementing with our entire team. We'll give you guys tasks, give you guys deadlines, and everything should be completed in sprint. It's actually really fun. It makes writing code fun. You're doing little bits of code, you push them up, and then you all of a sudden you see functionality. And that's the best part of it. Go to the next one. So this is the components of our software. On a level just driven more towards the web app, it gets pretty simple. So the ARM processor is giving data to the Raspberry Pi. The web application is going to be sending and receiving commands through Node.js. So what you see here is Node.js establishing a connection to the WebSocket. And like I said, WebSocket is bi-communicational, so you can get data, send data, and it's real time, pretty much real time. It's like what, 10 millihertz?
We can So by testing on campus, we've noticed that the delay is about less than 10 milliseconds, which is what
Pretty
SpaceX
good.
requires us to have the minimum delay that they need information on when you're running through the journey. They want information at every 10 millisecond pulse. So we're able to hit that mark, so which means that WebSocket is something that is going to work for us. And that's again assuming that SpaceX has a really good network, but that's not on us if it doesn't work there. If it works on Sac State and we can prove it to them, then we're good.
So we're looking for front-end developers to help program. Once we get data, it should be rendered onto the front end. All that requires is HTML knowledge, some CSS, and some JavaScript. The JavaScript can either be Angular or you can just write some plain old JavaScript jQuery. It's really easy to pick up. The backend is Node.js, and then some Python will be used for computation coming from the low-level side. Prem can tell you a little more about that. But if you know JavaScript and you know how the events work, if you know, your object-oriented programming, it's going to be really easy to pick up on JavaScript and learn the syntax. We're also looking for people to break our code. We're going to be writing code out all day long, so we're going to need people to break it. Because once we get to SpaceX, they're going to stress test us really, really bad. So we're going to want the best people to break the code as well. And Scrum Master pretty much just means somebody that will be managing our tasks. So if you understand code logic but don't really feel comfortable writing code, but you feel comfortable managing a project, that mostly is going to be done by Prem and I, but we could definitely love assistance on managing Scrum too and making sure everybody's up to date on their tasks, like going out and reaching out to the each individual developer and making sure their code has been done.
So now this is what is actually trying to combine the low-level architecture and the information coming from the server side. In order to achieve this, we have a 6-state finite state machine. What this is, it's basically going to keep track of all the data that's coming in for a given instance of time. So, for example, when you're starting the pod and it's basically a time 0, that's what we count as time 0. When the initial power-up comes on, that's time 0 for us. And then we go into idle. It knows a predefined state, so it's going to stay in idle, and then it's going to go through the whole startup sequence, read from every sensor, check with the predefined value, know that it's working. So that way we can ensure that every single sensor is on and it's reading the right value. From there, we're gonna move into the tube, which is going to take about 30 minutes for SpaceX to build the pressure down from 1 atmosphere to 0.125 psi. And then that takes about 30 minutes of time. So we're just going to be sitting inside the pod, and then it's going to be, that's the state it goes into. It's going to go into the state called ready. And it's going to stay there till we see an initial acceleration. The acceleration is when the pusher interface starts pushing the pod. That will be anything greater than a 0.1 g. That's the regular thing. And initial velocity is 0, final velocity is nothing but 0. Then we start going and we move to the state called pushing. That's where we spend about 5 to 6 seconds, where that's the 1500 feet being covered by SpaceX. And after that, we're going to move into coasting. That's where the entire control system has to definitely kick on and make sure the pod can deliver. We'll be monitoring various sensors. We'll be monitoring sort of a machine learning algorithm, if you guys are interested in that too. Trying to predict that if something could go wrong and make sure that we can compensate for that if we start to detect any faults from reading from sensors. Like let's say we're going to be sampling the sensors at every 100 milliseconds. So it gives you enough data points. That's about 17,000 data points in a single run. And if you can sort of create a learning algorithm as it progresses through the whole journey, we'll be able to compensate any faults that are coming from sensors. If one of the sensors fails, we'll still be able to compensate for that, which is something that SpaceX is looking for. How safe can you make a pod? And how can you make sure that if one of them fails, how you compensate for that? And then from there, about 2,500 feet from the end of the pod, we're going to start braking and then eventually come to a halt and then go back to idle so the pod can repeat itself. In any of these states, if you see a fault, if it's a hard fault, like if a malfunction of a hardware and it can no longer function, then it's going to send a fault byte to SpaceX and also bring the pod to a halt. This is the software architecture. What this is it's basically building a wrapper module between the MongoDB and the low-level architecture. It's written in Python because of the development of many libraries that are out there, and also it being closer to object-oriented programming and being able to port it onto various devices. Now, that's why we picked Python. The main purpose of Python is to establish communication between the low level and MongoDB, also be able to keep track of all the sensor data that's coming in. It can also issue commands to the microprocessor saying if one of them is wrong, kind of reacquire the data or issue breaking if need be. This is the hardware. Um, so what it comprises of two main systems. One is the RPi, which is called a mini computer. The other one's a microprocessor. That's how the microprocessor looks like. It's powered by an ARM Cortex M3, has 72 GPIO pins, and it has a inbuilt ADC channel. Also has communication protocols like I2C, UART, SPI. We also have an Ethernet capability, so if you want to directly tap into the microprocessor, you can do that too. And this is our RPi, capable of hosting a completely Linux-based operating system. And here's our main channel that will establish communication from low level to the high level. We can run data on this channel at 1 megabits per second, which is at a speed of less than 10 microseconds. So you can ping data across at less than 10 microseconds. So that's really fast means of communication, and it's close to real time. And these are sensors. There are 18 sensors on pod. These are various locations. The ones you see pointing down right here, these are the proximity sensors to find levitation height. The sensor right here, this is pointing in the front of the pod to figure out what the distance is from the end. We have 4 sensors mounted up. Those are retro reflectors. What they do is they keep track of the tape that SpaceX provides us on the tube. So you can sort of a mile marker. You read those number of markings, then you can find out how much you've traveled or how much is there to travel yet. And then you can estimate velocity from there too. Here's our battery bank. We have temperature sensors inside those, and we also have a temperature sensor inside the pressure chamber. Again, these communications, most of them are analog, I2C, RS-232. These are all low-level communications. Any questions? Yeah. Yeah, we're developing right now. So he's going to show you what we have done so far. So we have the RPi set up. We have the server set up on it. We're working on trying to pull data off it, which is trying to get it onto a real-time web page. He's going to talk about it more and
We've
show you
already
a demo
started, though.
too.
To answer your question, we've already started. We're all meeting on our own ends. We have people working on super low level in the middle. Like you saw the diagram of the different connections. So we have to have the sensors communicating with the processors communicating with the RPi setting up a server with the database sending it down to the website sending commands back up. Each one of those channels are going to be attacked individually, and we're working on that right now. We're all starting from one end and hopefully meeting together. But it's been started, yeah.
About 10 people.
For the controls specifically.
We're just controls.
In total, then it's about like 40 or so.
The full stack, there's only
Full stack meaning all the entire software. Yeah, 3 of us. Not even. I think just myself right now.
I was helping out a little bit in the beginning, but then I have the low-level architecture to take care of, so I can help answer questions on a really high level, like how things are connected. But in order to actually physically implement the code, he's the only one who's writing code for that. Yes.
Yes. Yes. After this semester we'll be done. This is done in the summer. We need help now.
Like I said, we gotta run it down there over and on. Yeah. So we gotta do this like ASAP. We gotta run it down.
Pretty much, yeah. I mean, even if anybody can come on and contribute a good chunk of code, that's a lot of experience that you're getting. It's pretty much a job. Like, I wrote it down as a job on my resume. I work for Hornet Hyperloop. I do this for them. And people have already asked me a bunch of questions, and it's really valuable. Even if you can come on for 2 months till the end of the semester.
You still work over the summer.
Yeah, and I plan on working for the summer, so yeah. We can get you the information after we kind of answer more questions. We'll be here.
Yes, you could.
Oh yeah, these guys work all the time.
I do 4 sessions to accommodate various time slots. I do Monday, Wednesday. That's where we can actually access our new room that's on campus. But we also do other time slots. I do it on Tuesday. Yeah, I'm flexible. Yeah.
And a big.
No, we have a whole bunch of meetings.
Yeah.
I think we got like Tuesday for powers at 2, and then we got like another Tuesday at 2 is structure, and then Tuesday at 4 is the power, and then we also got like another couple for other structure, and then we got another one for transit. We got another one for office meeting. We have a whole bunch of meetings.
And you meet in
We
between.
meet, like individually with
Yeah.
these guys as well. So we also have like Slack. So, like they mentioned beforehand in the previous meeting, we use Slack in order to be able to communicate and everything. We also use Google Hangouts if you want to just like fast talk on there, so we have that integrated into Slack.
Yeah, our communication is really good, and if anybody's on campus, they're always trying to meet and get work done. So any time window you guys have. So.
We had people from 6 a.m. up until like 1 a.m.
And a big thing is, if any of you guys don't want to join because you don't know Node.js or you don't know HTML, I'm about to solve that problem. I just paid $20 a month for a giant, it's called Code School, and so there's like 300 different Code Academy classes that you can take, and I'm paying money out of my pocket. I'm willing to share with you guys my password. I don't mind if you will come on and actually learn and contribute. You guys can have my password, complete all the courses. I don't care, as long as you're helping out with Hyperloop.
Also to mention regarding the integration of the entire project, we have a pivotal tracker. What it does is it integrates between your Google Drive, GitHub, and Slack. So if you type something in Slack and you tag it with pivotal tracker, you can mention what piece of code you pushed it up or what project what kind of a side project you're working on, and then that will tie it into the GitHub, and it can also mention that when you're typing it out in Slack. So you don't have to pass multiple links at the same time. It's already integrated into one single point of channel communication.
Yep. So if you check in a piece of code, our entire team automatically know, oh, this guy just checked in a piece of code, review it, and bring it up to the master repo. So it's really, really robust. And like I said, I've had a few internships, and that's where I've learned these industry standard procedures. So these guys had it already integrated before I even got on. Prem knows a lot. Our team is super, super knowledgeable. I mean, even I didn't know how I was going to approach Prem with this programmatic knowledge coming from a low level end, was able to actually help me out a lot, even though I'm a high level programmer. So, any more questions? Keep asking some. Keep asking some.
So you're talking about the showcase that we did over there. So on January 29th, we went over there to be able to showcase some of our efforts out there. We had like our design that was only preliminary at the time. We were submitting our final design report and presentation with the leader, with the leader, and finish that up. But over there, then we also had some augmented reality photos, some virtual reality, also our HDK. However, that was jacked out of my car just like 2 weeks ago. So that was basically a small little levitating system. So it was actually able to rotate magnets kind of similar to the same environment that our pod is going to be operating under. And then some other, like we had some other documentation. So we had the funnel for preliminary design presentation going, as well as basically other preparation docs. So how we're going to be putting the magnets together, a little bit more on the mechanical side. For our report, we have a 247 page.
Do you wanna show them the web page?
Yeah, you want to just run it on there? How do I do that? Just type in the.
Basically outlining most of the stuff that they said over there.
All I did was put. Get out of here. All I did was put that in my browser.
Oh, so and then it'll automatically do it because I don't have it page.
Just put that in your browser. We're on the school network.
So it's directly gonna ping. Oh, okay, nice. Let's do that then. You wanna do it?
Yeah.
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 And yeah, they seem to definitely enjoy it, and they certainly were very interested in our controls.
Oh, here. I got the mouse.
It's alright. 10.
Okay, so right now what we're showing you is we're directly pinging to the RPi that's on campus network. We're going through the whole full communication protocol and then getting to the server web page. So that's the server web page that's hosted on RPi right now. It's directly connected at the back PC, and we're able to see it. I mean, right now there is no data that's coming into the RPi, so it's not updating in real time. It's static right now. But we're gonna move this about to make it look like how you saw it on the front end page.
It doesn't have to look exactly the same. So we're using a framework called Bootstrap, and so Bootstrap is a set of predefined CSS components that you can use in a website and manipulate all you want. So these are kind of like predefined in the CSS, but we want to like shrink it, add a picture of the Hyperloop, maybe make it, you can add some interactivity. So those are all things that a front-end developer would help us do. It's very easy. Like this is probably no joke, guys. This is 5 lines of code to make this thing appear. Really,
and again,
really easy. Really easy. It's literally just box class equals box 2 or 3. It depends what the CSS rule is. It's super easy, and the box appears. You just put some data and it appears. It's a table. Super easy. And to add some functionality, it's nothing more but add this variable when it gets updated. It's super easy. Easy to learn. Not going to be easy to implement if you don't know what you're doing, but it's easy to learn, and if you're driven, it's going to happen, and you will be very rewarded once it happens.
Kind of a, like I said before, a pretty high profile kind of company. There's schools from all over, and they're all probably a little bit higher popular, or they're more popular than we are usually. So like there was the Edinburgh, there was like I forgot the list. Remember?
All the ones, no, but on top of my head,
Yeah.
we can pull it up. Just read out the list. The ones that I
Backstage.
know from India, it's Bits Pilani. Then there's Warloop from Germany, Netherlands. From California, we have University of Southern California. We have Sac State, Irvine, UC Davis, no, UC Berkeley.
Only the three.
Berkeley?
Berkeley is not in.
Oh.
They didn't make it.
Okay.
Davis didn't make it. There's a lot of schools that didn't make it.
Even Silicon Valley schools didn't make it. We are the Silicon Valley school to make it. So there's a lot on our hands. So if you guys want to be part of something big, this is what to be part of.
What? Yeah.
Yep.
The only one north of us is like another one that's like over by Portland.
But that's Washington, so.
Yeah. So we can even like that take some territories over north. Yeah. All of Nevada, and there's a whole bunch of like different places that we try and get in contact with. Which is kind of another thing. If you guys need other software or hardware or whatever, what's kind of nice about the competition, and especially now that we've made the final cut, they look at it and be like, okay, yeah, we'll give you stuff, so let's put our name on it, you know, whatever. So we could probably get like whatever for free or for heavy discount. So kind of one of the cool things. I think we got like 3 fucking cents in the past 7 days. Yeah.
You'll be talking to engineers like I went to a conference last weekend, like we have one Hyperloop team, and then they go, oh, didn't only 24 make it? Yeah, we're one of those 24. And it's like a really good thing to say. I know I can't say I was there from the start. I just joined like after the FDR, but it's something big.
Definitely like to hear it. Because it's like cutting edge, and really, like I said, there's only 24 in the world that actually pretty high quality.
It was on the front page of Yahoo, I want to say the other day. My dad doesn't know anything about tech, and he was like, hey, I just saw 24 teams made it. Yeah, that's one of us. So.
Like on all the news sites.
Yeah.
Yeah, we also got like featured on and a couple of yeah.
Thanks for listening, guys.
Any other questions? Pretty much contact you guys.
So I hope one of these. I think there might be a couple that seem really interesting.
If you guys really want, we can sign you up on Slack right now. Just go through my computer and invite. Okay. Cool.
Alright, let's do it.
What were you interested in? Do you know, or were you kind of want to? Okay, yeah, hell yeah.